Hello everyone, my name is Anjum. The topic is impact of large scale correlated failures on multi-level virtualized networks. Introduction to multi-level virtualized networks. Multi-level virtualized networks encompass multiple layers of abstraction integrating physical, virtual, and service layers. They are crucial for supporting modern cloud services, data centers, and telecom infrastructures. Understanding failure impacts in these complex systems is vital for ensuring reliability and resilience. Overview of large scale correlated failures. Large scale correlated failures occur when multiple network components fail simultaneously due to common causes. These failures differ from isolated faults by their widespread impact across the network. Examples include natural disasters, power outrages, and cyber attacks affecting multiple nodes concurrently. Significance of studying failure impacts. Studying these failures helps identify vulnerabilities in multi level virtualized architectures. It enables the development of more robust and fault tolerant network designs. Understanding failure patterns guides the implementation of effective mitigation strategies. Components of multi level virtualized networks. Physical layer includes hardware components like servers, switches, and storage devices. Virtual layer abstracts physical resources into virtual machines, containers, and network functions. Service layer delivers end user applications and services over the virtualized infrastructure. Causes of large scale correlated failures. Natural events such as earthquakes or floods can simultaneously damage multiple physical components. Power grid failures can cause cascading outages affecting large sections of the network. Cyber incidents like coordinated attacks can target multiple virtual or physical nodes simultaneously. Impact on physical layer. Physical layer failures can lead to loss of hardware resources critical for network operation. These failures often cause cascading effects disrupting virtual and service layers. Recovery from physical failures can be complex and time consuming, impacting service availability. Impact on virtual layer. Virtual network functions may become unavailable due to underlying physical failures. Virtualization platforms can experience degraded performance or complete outages. Large scale failures hinder resource allocation, affecting multiple virtual network slices simultaneously. Impact on service layer. Service disruptions affect end users, leading to degraded quality of experience. Critical services like Vivo IP, streaming, or cloud applications can be entirely unavailable. Downtime impacts organizational operations, revenue, and customer trust. Cascading failures in multi level architectures. Failures in one layer often propagate to other layers, intensifying the overall impact. Cascading effects complicate diagnosis and recovery efforts. Understanding these cascades is essential for designing resilient architectures. Modeling large scale correlated failures. Probabilistic models estimate the likelihood and extent of correlated failures. Dependency graphs illustrate how failures in one component affect others. Simultation simulation tools help analyze potential failure scenarios and their impacts. Resilience strategies in virtualized networks. Redundancy at physical and virtual layers mitigates the impact of failures. Dynamic rerouting and resource reallocation help maintain service continuity. Legal testing and failover procedures enhance overall system resilience. Fault tolerance mechanisms. Distributed architectures enable localized failure management, checking point and recovery protocols, restore services after failures. Advanced monitoring detects early signs of correlated failures for proactive response. Impact of network topology on failure propagation. Dense and meshed topologies can contain failures better than linear ones. Hierarchical multi-level structures influence how failures cascade across layers. Designing resilient topologies reduces the risk of widespread outrages. Case study: natural disaster impact. Example of a regional earthquake causing simultaneous physical and virtual layer failures. Disruption of multiple data centers led to service outages across cloud providers. Lessons learned emphasize the importance of geographic diversity in disaster recovery planning. Cyber attack scenario. Coordinated cyber attacks targeting multiple virtual functions can cause large scale failures. Attack vectors such as distributed denial of service amplify the impact. Implementing security measures reduces the risk and impact of such correlated events. Challenges in mitigating large scale failures. Predicting correlated failures is complex due to diverse causes and propagation patterns. Ensuring redundancy without excessive cost remains a balancing act. Coordinating recovery across multiple layers requires advanced orchestration and management. Future directions for research. Developing more accurate models for failure correlation and propagation, leveraging artificial intelligence for real time failure detection and response, designing adaptive architectures that dynamically reconfigure during large scale failures. Conclusion: large scale correlated failures pose significant risks to multi level virtualized networks. Resilience depends on understanding failure mechanisms and implementing robust strategies. Ongoing research and technological advancements are essential to enhance network survivability. So, summary of key takeaways. Correlated failures can cause extensive service disruptions across multiple layers. Modeling and simulation are vital tools for understanding and mitigating these failures. Building resilient architectures requires a combination of redundancy, monitoring, and adaptive mechanisms. Thank you.